In this video, we're going to apply integration by parts to help us compute the antiderivative of the ln of x to the 1/3. Now, typically when we think about integration by parts problems, we typically think about having two functions sitting there in the integrand. One of those functions will differentiate, the thing that we call u. The other piece will antidifferentiate, the piece we call dv. However, when we take a look at this integrand, we really only see one function sitting there, that ln of x to the 1/3, which at face value, this would suggest we can't apply integration by parts. However, we can always think about that second piece, namely that dx, as being the thing that we antidifferentiate. Since you could imagine that in front of that dx, we still have a 1. So let's actually go through this. So we have our two pieces. We have that ln of x to the 1/3. We have that 1 dx. And I sort of suggested a moment ago, well, that 1 times dx, that's actually going to be our dv. The piece that always has that dx attached to it, that'll be the piece that we antidifferentiate, which means the function that was originally just sitting there will be the piece that we differentiate, or the piece that we call u. So let's actually go ahead with that. So remember, we have our u. That's going to be the thing that we differentiate. In this case, it's ln of x to the 1/3. The other piece that we have is the dv, and that's the piece that we antidifferentiate. In this case, it's just equal to 1 dx. So we'll go ahead and differentiate the u, antidifferentiate the dv portion, and find all the characters we need for the integration by parts formula. So let's actually just go ahead and start on that the right-hand side. We integrate both sides on the left-hand side with respect to v. So the integral of, well, 1 times dv with respect to v, that's just v. On the right-hand side, the integral of 1 with respect to x, that's just going to be equal to x in this case. That left-hand side, and that now we're done kind of doing the antiderivative portion. Now we get to take the derivative, which means now looking at that u and taking the derivative of it with respect to x. So taking a derivative of u with respect to x, this looks like it's going to take a little bit of work. Again, we have the ln of another function. So this is looking kind of like a chain rule type aspect, since we have the ln of x to some power. And we apply chain rule, we work from the outside moving in, which means we differentiate the ln portion first, and then kind of keep going through our layers of the onion. So first we differentiate an ln, which means we take what's ever inside of that ln, in this case, the x to 1/3, and we put that in the bottom of a fraction. So we take 1 over what's inside of that ln, in this case, 1 over x to the 1/3, and then we keep moving inwards. So the next piece that we have to this chain rule operation, when we pass the ln stage, well, now we need to differentiate what's inside of that ln. In this case, it's the x to 1/3. And since we have an x to 1/3, or an x to a power, we get to apply the power rule, which means that 1/3 that's sitting there, when we apply the power rule, that's going to come down, act as a coefficient. We're going to subtract 1 from that power then. So in this case, we have that 1/3 then being multiplied on times x raised to the, well, 1/3 minus 1 power. So I'll clean this up in a moment. So we have our du dx, or derivative of u. This thing's equal to, well, 1 over x to the 1/3 times that 1/3 coming from the power rule times x to the 1/3 minus 1 power, or the minus 2/3. All right, so we're almost at the stage to use our integration by parts formula. However, the formula that we need is in terms of du, not du dx. So we'll actually just kind of kick this dx over to the right-hand side through cross multiplication. So if we go ahead and do that, we get our final du, which is equal to 1 over x to the 1/3 times a 1/3 times x to the minus 2/3, and then times that dx. So if you remember correctly, the reason why we need a u, we need a du, and we need a v is because all of these characters are in our integration by parts formula. So the integration by parts formula, we take what we have for u, we multiply by that v, and we subtract the integral of v du from it. So the next stage that we have for our integration by parts formula is really just plugging in everything we found. Everywhere there's a u in our formula, we plug in a ln of x to the 1/3. Everywhere there's a v, we plug in x. Everywhere there's a du, we plug in that complicated looking derivative. So let's go ahead and plug that stuff in. So first we plug in for u, we have the ln of x to the 1/3. We plug in for v, that's giving us an x. And then we subtract from it the integral of v du. Again, v is x, coming from our relationship up there. And we found for du, that was that complicated looking kind of derivative that popped out more or less. But we'll see in a moment that we're actually going to be able to simplify a whole lot of this remaining integral. So we have 1 over x to the 1/3, a 1/3 coefficient, a x to the minus 2/3, and last but not least, that dx. So we've applied integration by parts here so far. We have, well, some product of functions sitting out in front. That just is what it is. But we still have an integral here that we get to do. And our hope again is that this integral that's left is easier than the original integral. This thing looks a little complicated, but the one thing we can notice, there aren't any ln's in it, like there were in the original integral. And we only have sort of x to power stuff, which means we're going to be able to simplify a lot of this algebraically. So let's go ahead and do that next. So this first product of functions, I'm just going to rewrite with that x in front as x times the ln of x to the 1/3. Next, we can subtract the integral. And I'm going to actually take this 1/3 coefficient and just move it in front of everything else. We have an x to the first power coming from that x that's just sitting there. We have an x to the minus 1/3 power, since that we had originally a 1 over x to the 1/3, which means we could equivalently rewrite that as an x to the minus 1/3 power. And then finally, we have that x to the minus 2/3 power times dx. And now, since really what we have are just x to powers being multiplied all together, we can add their powers all together. So that'll be the next step we do. So that first product, x times ln of x to the 1/3, that remains unchanged. I'm just going to take that 1/3 just completely out of that integral, since it's just some number that doesn't depend on x in any way, of course. So we can pull it out of that integral. And next, we really just have the integral of x to the first. And since we're multiplying a x to the minus 1/3, we subtract a 1/3 from that 1. And since we're then multiplying an x to the minus 2/3 power, we subtract a 2/3 off of that as well. All right, so we're almost there at the simplified integral. Again, that x times ln of x to the 1/3 remains unchanged. We have minus 1/3 now times the integral of x to the 1 minus 1/3 minus 2/3. So that is x to the 0th power. And we're going to integrate that with respect to x. Now, an x to the 0th power, we can rewrite as just 1. So just go ahead and do that. Again, any number raised to the 0th power is equal to 1, except for 0 to the 0. So this integrand actually simplified very nicely for us. We just get to integrate the number 1 with respect to x. So this antiderivative turns out to be x ln x to the 1/3 power. Again, that piece remains unchanged, minus 1/3 times the antiderivative of 1 with respect to x, which is just an x to the first. And then lastly, we tack on a plus c. And that would be the antiderivative of the ln of x to the 1/3 power. Again, the piece that I would like you to take away from this video is looking at that original integral, we only had one function seemingly inside of that integrand. But we could try applying integration by parts, knowing that that piece in the integrand is the part that we can call u, the piece that we differentiate. And the piece that we anti-differentiate would just be that dx, or you can envision it as a 1 times dx like we did here. And you can always try this when we have a one single function inside of an integral. Sometimes this will work for things especially like ln's or for arctangents if they're sitting there by themselves, but sometimes this also may not work. But it's another way that we could apply integration by parts to integrals that don't right away kind of scream integration by parts at us.